high schedule and only have an hour for quiz talk and then only 10 minutes for coffee break, then another session, regular session going on. First of all, I would like to welcome all of you to Taipei. A little bit humid, but temperature is not that hot, so I enjoy it all, I guess. Also pollution a little bit better because of the rain. Come on and ask me to announce, first of all, is there's some time schedule for those of you who are living in downtown hotel. Every day, the bus in the morning will pick you up, and the time is 7:20. Okay? So next couple of days, 7:20, the bus will wait in the hotel, and so you can just take that one. For the time to get back to hotel, maybe that's more flexible. Usually that's when they arrange the bus back to hotel after dinner. So I think should be all right. Let's start this session. We are glad to have Christians to present the first invited session for us. It's really exciting to see him again for many years. And Chris very well. He's our past president, 1995 of the Econometric Society, and also the president of American Economic Association, 2012. The most important one is the Nobel Prize with Tom together. That's really exciting. And Nobel Prize 2011. And I know Chris for some quite long time. In Minnesota, Chris has been in Minnesota for 20 years before he moved to Yale and now in Princeton. And Chris is really a great scholar and educator. I feel exciting when I start my career in Minnesota, and he's my senior mentor, give me a lot of help, I appreciate. And also a lot of students learn a lot from him, including Lars Hansen. During that period, I think Minnesota really have a golden period. We have, so-called four horsemen there, Chris, Sargent, Leo Ors, and Ed, so people call them four horsemen. Also, we have a strong theorist, Hurwitz, Leo Hurwitz, so all are Nobel Prize winners. And also we have good students, something like Hansen. So at that period, I'm lucky to have the chance to witness, for example, discussion of GMM between Chris and Lars, all the things. So that's really exciting about that period. Chris, all much of his work than I do. He's an econometrician, but also a great macroeconomist. What's special about him is he brings reality into macroeconomics and use macroeconomics to face reality. So we'd like to hear today what he talks about macroeconomics and guide us what the economy should do. Thank you much. Yeah, please.
Get the slides there. I'm very happy to be here. Thanks to the Econometric Society for inviting me. Great chance to get to Taipei, which I've only been to once before. That golden age at Minnesota really was golden, and it is true that I work on macroeconomics and reality and econometrics. Today, though, I'm going to talk entirely about microeconomic theory, which maybe is a disappointment to you, we'll see. It's motivated by macro issues. So how do I get it to, oh, there it goes. So this is a talk about Shannon capacity constrained behavior, which is, I'll define in a minute for you what Shannon capacity is. And the main point here is to go beyond the cases that I've discussed in a couple of previous articles where you look at linear quadratic models, Gaussian errors. Those models are, in the first paper I wrote about this called Implications of Rational Inattention in the JME, I considered those cases and got some insight from them for macroeconomics. But after that, I started trying to consider cases where the underlying uncertainty was not Gaussian and the models had nonlinearity. And I approached them numerically and ran into lots of difficulties. They seemed to be very intractable. And over the past 3 or 4 years, this paper that underlies this talk has been evolving as I and some students have slowly gotten better ideas about how information processing constraints interact with traditional decision theory. So the original motivation for my looking at this was macroeconomic time series. When you just estimate reduced form dynamic models for them, the typical impulse responses you see, if you just do a Cholesky ordering, show a substantial weight at zero lag for own shocks, which means that most of these time series do not look like samplings from differentiable paths. They jump around. Their derivatives are very erratic. And yet at the same time, cross-variable responses, when they're non-trivial, tend to start low and be hump-shaped. And that's a generic problem. In macro data, cross-variable reactions are smooth and slow, and so structural models that attempt to match that have traditionally introduced adjustment costs to imply that changing rapidly in response to something, to like a price signal or an interest rate, is costly, and that's why we see only smooth and slow reactions. But adjustment costs by themselves actually imply that own responses should be smooth too. They imply if it's costly to change the derivative of something, the time path is going to be smooth and differentiable. It's not going to involve, it's not going to look like the time path of a Wiener process. And yet actual economic time series, macro time series, do look locally like Wiener processes for the most part. And then there's just intuition and micro stylized facts. Most people, most of the time, do not respond immediately to price signals, and indeed may not even be fully aware of price changes. Ask yourself, if you own a car and have bought gasoline, can you remember what the price of gasoline was the last time you bought it? Did you actually do what I'm describing here? For example, a person driving down Route 1 in New Jersey has many opportunities to buy gas, and the prices are posted on large signs so as she drives by she can see them all. A fully rational agent has a complicated dynamic problem. You should be keeping track of the price distribution and the amount of gas you have left in your gas tank and continually re-optimize and pick just the optimal place that looks like it's at a low price in the distribution. But an actual person driving down Route 1 is probably listening to the radio, talking to somebody else in the car, and not noticing most of the prices, and when the out of gas light flashes on, just stops and buys it, whatever the price is, without even looking. But that's not rational economic behavior if you don't take account of the fact that talking to your friends and listening to the radio actually may not be consistent with solving a dynamic optimization problem concerning when and at what price you should buy gas. So it seems realistic to recognize that even freely available information is sometimes ignored because processing it is in some sense costly. An economist wants to include this cost in the rational agent's decision problem. But how should we measure such a cost? Claude Shannon had an answer. If you believe that information flow should be modeled as reducing uncertainty about some random quantities, and if you believe that information flows from observing two random quantities in succession should add up to the amount of information in observing the two random quantities jointly, you have essentially no choice but Shannon's measure of mutual information to use as the measure of the cost of information. Shannon's measure is all around us. We're used to measuring the speed of internet connections in megabits per second. That's a measure of the maximal rate of information flow over the connection in Shannon's units. And I meant to add here, one of the important things about Shannon's measure is it doesn't ask, what are you sending? We know that this is a meaningful measure of information processing capacity, regardless of whether you're sending photographs, videos, text, sound. They all transmit at a higher speed if you have more megabits per second, so we don't get specs for our internet connections that say here's how fast it goes for sound, here's how fast it goes for pictures, and so on. They're just one number. That's Shannon's capacity. So if you add to an individual decision problem a statement that observing external signals and translating them into action involves information transmission through a channel in Shannon's sense, and that if we think of an individual person as somebody who has to translate signals into actions and has a finite capacity in Shannon's sense for converting observations on a random signal into actions, then you get a well-defined optimization problem. And in fact, what I showed in that earlier implications of rational inattention paper is that it implies both non-fundamental noise in actions and a smooth and delayed reaction to fundamentals. And you can get that out of the linear quadratic case, and that's what I discussed in the in that implications of rational inattention paper. So now in this paper, which is joint with 3 Princeton graduate students or former Princeton graduate students. I should note that on the program, Matejka is listed as at Princeton, but he's now at CERGI in Prague. Jung and Kim are students at Princeton. Jung is actually a mathematician, not an economist. In this paper, we are getting outside the Gaussian LQ case and trying to understand the complex patterns of results we've gotten in those cases. We began these, Matejka's thesis solved several interesting problems numerically that were outside the linear quadratic Gaussian case. And what he observed there and what I observed in a paper that was in the AEA proceedings several years back is that numerical solutions tended to look discrete. That is, you set up a problem where we can solve it analytically without the information processing constraint. You put in some random variable that influences the decision that's continuously distributed. In the case without information processing constraints, individual behavior is also continuously distributed. You add the information processing constraint, and the result is you get a discrete distribution. Actions just move around amongst a finite set of points in the possible action space instead of being distributed discretely. And this is without any non-convexities, without anything that would directly produce discreteness in behavior without the information constraint. Now we know there are cases like the linear quadratic case where this doesn't happen, where the actions are continuously distributed. So the task we've set ourselves is to try to figure out, to see if we can say anything in general about these issues of when do we get lumpy behavior out of information processing constraints. So we consider this static information constrained decision problem. In previous drafts of this paper, which you may find posted, we considered only what are called tracking problems, where the objective function depends only on x minus y, on the difference between a decision and an action. Tracking problems of the form I'm setting up here are exactly what engineers have studied under the heading of rate distortion theory. And there's an information theory literature on that. Most of rate distortion theory considers only x minus y quantity squared as the objective function. We're trying to generalize that, partly because most economic problems produce u's that are not simply quadratic. So you have an objective function u of x and y. X is the thing you're going to choose. Y is a thing which you don't know, which has a distribution, and it's going to cost you to reduce your uncertainty about that distribution. So the objective function is is the expected value. F is the joint density of your decision, your action, and this external signal y. We assume this doesn't have to be continuously distributed, so mu y is the base measure for in y space for the density, and mu x is the base measure in x space. Mu x is part of what you choose. You choose whether to have Lebesgue measure as your base, or instead say a discrete measure or a mixed continuous discrete measure. And F is the density with respect to this base density mu x times mu y. Then the alpha inverse is the cost of information. And this thing in parenthesis, this whole expression is Shannon's measure of the mutual information between x and y, which is a function of the joint density F. If you're familiar with the idea of entropy, this is saying this one is the entropy of the marginal distribution of y. This is the entropy of which is which? This is the entropy of the marginal distribution of y. This is the entropy of the joint density. Should be the entropy. This expression may not be right. So let me tell you what it should be. It's the difference in entropy of the distribution of y, of the marginal distribution of y, and of the conditional and the expected entropy of the distribution conditional on your decision x. So it's describing the average. If you treat entropy as the measure of how much uncertainty there is in the distribution, this is Shannon's measure says it's the expected reduction in that uncertainty that describes the mutual information between x and y. This results in a situation where when x and y are independent, so f of xy is f of x times g of y times f1 of x times f2 of y, the mutual information is 0, and the mutual information goes to infinity if the xy distribution collapses on the x equals y line in a continuously distributed case. Now it's very important that there's also we also, we're picking what we're doing here is picking the joint distribution. This is a standards decision problem, but we're not allowed to pick x. We're allowed to pick the joint distribution between x and y. A way to think about this that people may find more intuitive is to say you're allowed to pick a signal about y, and your action x is going to have to depend on that signal. You get to choose the distribution of the signal about y subject to this constraint as a constraint on the accuracy of that signal. And then your actual action, you can choose your action directly, but as a function of this noisy signal. So you're going to choose this joint distribution subject to the boundary condition that the joint distribution has to add up to the given initial PDF of y that describes your uncertainty before you do any information processing. And then this thing is very important. The joint density has to be positive everywhere. This is a completely nicely behaved problem. This objective function is concave. In fact, the first part is linear in f, so it's a nicely behaved problem where first order conditions are going to define the solution. The trouble is this condition in a continuously distributed problem, infinitely many of these boundary conditions are going to be binding. And that's what makes it computing the solutions hard. You can't just say, let's do the first order conditions. Every once in a while you hit a problem where the first order conditions, ignoring this boundary constraint, give you the answer, but all the interesting problems that we're dealing with in this paper are exactly the case where these conditions bind, and the hard part of finding the solution is finding which ones bind. So if we just take first order conditions, it turns out, I'm not going to go through the details, but you get this out of the first order conditions, which implies that the joint density, this is not C of x. The joint density can be written as P of x e to the alpha u h of y. C of x is the integral of this object over y. H is something that is a function of Lagrange multipliers, but it's positive over the range where G is positive. P is the marginal density for X. It's the thing that's actually the subject of interest in this paper. We're interested in we're interested in P and in mu X. Are we going to get a discrete distribution, or are we going to be able to get a continuous P of X over the whole natural X space? It's also true that when we integrate this thing over X, it's got to come out to be G of Y. So the one possible case is where the P of X greater than or equal to 0 never binds. You can pick H constant so that the conditional distribution of y given x has the form of e to the alpha u of xy. That's the nice situation. It's the one that Shannon showed that in the quadratic case, that gives you you can calculate the mutual information for that case without knowing G, and that gives you an upper bound for how well you can do. But all these conditions have to hold only where f of x and y are greater than 0. When f of x, y is 0, these things can break down. And the whole trick is to figure out where and why we get the zeros in P of x. So that function C of x, which is, as I said, the integral of f of x integral of this P of x e to the alpha u h of y. Now C of x, f of xy is 0 at some points. And then the first order condition doesn't have to hold. This is really badly written. C of x is this thing everywhere, whether f of xy is 0 or not. It's a function of x that's just the integral of this thing over y. Now that function, C of x, has to be 1 wherever p of x is greater than 0. And in fact, I don't know why I put C of x in there at that point in the equation. C of x is the integral of this thing without the p. It's integral of e to the alpha u h of y dy. And that has to be 1 wherever p of x is positive, because it is, wherever p of x is positive, it is the integral of the conditional density of y given x. So if we call B, the set of x values for which C of x is 1, that contains the support of x, because at every x that's got positive density, that integral has to be 1. If the objective function is analytic in x on some open set, then it's often fairly easy to show that C of x is also analytic in x over the same set. So then, the set B is either the whole of this open set, or it contains no open sets. Why is that? If C of x is an analytic function on an open set, if it's positive if it's constant over any open set, it's constant over the whole open set, if it's an analytic function on an open set. So, if it's not constant, then if C of x is not constant, then the B set contains no open sets. So B is either the whole of S or contains no open sets. And when S is one-dimensional, B is either the whole of S or a countable collection of points with no limit points in S. That means if we can, by a separate argument, show that the support has to be in a closed set that's a subset of S, that the distribution actually has to be concentrated on a finite set of points. So here's some examples. I'm not going to go through I'm not going to even try to state a general theorem about when you get discreteness, but just show you some applications where we can say something based on arguments that I've hidden from you, that are based on looking at that C of x function and proving it's analytic, and proving then either that it is constant or it can't be constant. Here's a simple case. This is one that was considered by Mateka in his thesis, except he used a different demand curve. But x is price, y is unit cost, u of xy is q of x times x minus, that should be y, not c. Q is quantity demanded, it's a minus bx. X is price, so it can't be negative, and it can't be bigger than a over b because the linear demand curve hits 0 there. So the price has a distribution which is going to have as a support a finite set of points. Then it turns out the price will have a distribution whose support is a finite set of points within the interval 0 to a over b. Now, Mateka solved this numerically in his thesis. He actually used x equals p to the minus theta as the demand curve. But the same arguments will work in that case. So the point is, once we know this, we don't have to know what A and B are. We don't actually have to know the distribution of C. As soon as we've got this set up, we know that we will have a solution that has price distributed over a finite set of points. So why is this interesting? Well, microdata on prices show that for a given product, they tend to remain constant for a while and then jump around between a finite set of prices. Some of the literature has tried to deal with this by saying, well, there are occasional sales, and we've got a separate model for the normal price, which is stable and has a menu cost associated with changing it, and the sale price, which is lower. But actually, if you look at the data in Eichenbaum and Rebello, and can't remember who the third author is, for a lot of products, you can see it's not just jumping up and down between a normal price and a sale price. It sometimes goes up to a standard higher price and then back to the normal price. It's really hard to explain that. Menu cost can tell you why price will stay constant for a while, but when you change it, you should react to all the available information. It should go anywhere. Why it should go back, and once it's changed, why should it ever come back to another price? Matejka's thesis showed with that exponential demand curve, you get, and you just have IID repetitions of this model, you get prices that stay constant for a while, and they tend to go down more than they tend to go up. So it looks a lot like the behavior we actually see, and could be explained by supposing that there are people setting prices who have lots of prices to set and lots of information flowing, and it's not worthwhile to them to react minute by minute to all the information flowing, and so they just have a rule that they make prices react to costs, but they go up to the higher price when costs are high and down to the lower price when costs are low. This doesn't mean that they have menu costs. It means they have information costs. It also suggests that you shouldn't be looking at you shouldn't have the idea that we could go to the microdata and look for what the real costs are. Go to the restaurant and ask, how much does it cost to print a new menu? That's not the issue. It's the information processing cost, not a physical cost of changing a price. One thing I may say it not, somewhere farther down the line here, but I might as well say it here. Shannon information processing costs never result in quantization. That is, they never result. This is not quantization. Quantization would say if the distribution has 3 points, there is a region of costs that are high where you make your price high. There's a region of costs that's medium where you make your price medium. There's a region of costs low where you make your cost low. And it's a simple rule. You look to see where the costs fall and then put your price according to that. These are discretely distributed prices, but the conditional distribution of costs given the price you've chosen always has full support. Meaning you choose, your price will be low when costs tend to be low, but there will be an error in your information processing cost that leaves some possibility that costs are actually high, even when you choose the low price. So here's another one. This is something that in the old version of this paper that just dealt with tracking, we couldn't handle directly. And this is where the first two co-authors came in. They showed us how to attack this problem. So it's really a CAP-M. In fact, what they did originally was just linear quadratic CAP-M, but we now can cover a more general case. You have an agent who has a fixed wealth of 1 to be allocated over a risk-free asset and a collection of risky assets. The weights that you choose are the vector x, and they have to sum to 1. The risky assets have random yield z, which have the form of y plus epsilon. Y is the Shannon-related uncertainty. This is uncertainty about the yields that you could resolve by processing information. Epsilon is hard uncertainty. No matter how much information either you can't get it just by processing information, or you'd have to actually spend physical resources, pay dollars to get the information for epsilon. So we treat epsilon as just exogenous. It's something you can't reduce uncertainty about by using your Shannon capacity. Y can, in principle, be reduced arbitrarily low to arbitrarily low levels by using Shannon capacity. And your objective function, u of x, y, is the expectation over epsilon of some utility function v of the total yield x prime y. So this is not, even when you use a quadratic objective function, it's not a linear quadratic problem because the payoff is itself quadratic. X prime y is quadratic jointly in the decision and the uncertainty. And so if you use a quadratic utility function, you've got quartic terms entering. But nonetheless, we can show analytically that the solution concentrates on a set of less than 2 dimensions. Why did I say 2 dimensions there? It's less than full dimension. Because I've talked about with 2 risky assets, with yields independent of each other and identically normally distributed, plus a riskless asset. So we have a 2-dimensional decision problem. The weights have to sum to 1, so there are 2 degrees of freedom. If we just solve this problem without the information processing constraint, those 2 degrees of freedom would be spread over the whole space of possible values continuously. Here, with 2 risky assets, we would get the solution concentrating on a set of less than 2 dimensions. In discrete cases, we get, in one-dimensional cases, we get discreteness because the only way to go from a one-dimensional space to a lower dimensional space is to go to 0-dimensional spaces, points. In higher dimensions, the analytic results we can get in general just say you go from decisions that are spread uniformly over a space of n dimensions to decisions that are distributed over a subset of that space that's of lower dimension. So here are some plots that show the weights on 2 risky assets when we solve this problem for the LQ case. And before I actually show you the plots, let me give you the interpretation so you know what to be looking for. When the information costs are high, the agent just chooses to go long or short on risky assets, and the relative weights on the 2 are the same. In this setup, the 2 risky assets are independent, but they both have the same distribution. Each one has this y plus epsilon, each has its own epsilon, each has its own y. But at high information costs, we find that agents simply, we don't put any short tails constraints. So they sometimes go short the risky assets, they sometimes go long the risky assets, but with the high information costs, they always change their holdings of the 2 by the same amount. And they just go back and forth between 2 portfolios. This looks a little bit like a phenomenon people see in asset markets called, you see it discussed in the press, that appetite for risk has gone up or gone down. People go into risky assets or out of risky assets. It's a little hard to see why this should be a pattern without information costs. With information costs, you get it with nothing fundamental in common about the 2 risky assets. People change their holdings in the same direction, despite the fact that there's no common fundamental component. At moderate information costs, the weights, you'll see that the weights get distributed over 4 points, corresponding to being relatively long or short risky asset 1 and being relatively long or short risky assets generally. At low information cost, the risky asset weights distribute on a circle. And in a plot I don't show you, but partly because it gets really messy, because the numerical solutions become very shaky at this point, but then it starts to look like it becomes continuous at very low information cost. So that's medium. Where is this? I've got, for some reason, the high information cost doesn't come out. But these are 2 plots that are really the same thing, except that the 3D plot shows how much probability is on each point, and in this graph, they're, I think, all about the same. Theta 1 and theta 2 are the weights on the 2 risky assets, can be negative, meaning you're shorting those assets, or positive. And you see that at this level of information cost, you're getting 4 points. At the high information cost point, you get just 2 points in the distribution, one at the lower left and one at the upper right. With low information costs, we get the solution spreading out around the circle. If we make it still lower, it starts to look like it's forming a kind of volcano with higher on the circle but spreading a little bit in either direction. This seems to imply that the sum of squared weights is staying the same until the information costs get very low. And I've been thinking that it should be possible for us to show analytically something like that, but we haven't yet. This is another kind of problem, linear quadratic tracking. You have an objective, you'd like to keep x close to y. A lot of models a lot of rational expectations, macro models, at least in the old days, used to set things up like this. You have an x star, which would be y here, which is moving around randomly, an x, which you're going to pick. And in a lot of these standard rational expectation setups, there's an adjustment cost on x that makes the optimal x depend on current and past y's and expected future y's. Here we have no adjustment cost, but we're saying that the mutual information between x and y, which is I of x, y, has a cost, theta. And we start with normally distributed y. And then the nice thing about normally distributed y and quadratic objective functions is that e to the alpha u, since u is quadratic, is the shape of a Gaussian distribution, and it's telling you that the conditional density for y given x in your solution should look normal. And this is, for normal distributions, those integrals that define the mutual information come out like this. They just depend by how much you reduce the log determinant of sigma. So this problem would be trivial if there were no information constraint. You just set x equal y, if a is positive definite, as we always assume. But with an information constraint, you won't make x normal, and the question is, what do you get? Now, you might wonder, where does the p of xy greater than or equal to 0 come in this? It comes in here in a nasty way. It's the difference between the log of the unconditional covariance matrix determinant and the conditional covariance matrix determinant that gives you your information cost. But it has to be true that the change in sigma from before you collect information to after has to be positive semi-definite. Another way to think of this is you're not allowed to trade off forgetting about some dimensions of variation in y for learning more about other dimensions of variation in y. And because of that, the problem becomes nasty. In the cases where the constraint that sigma minus the covariance matrix of x has to be positive semi-definite, when that constraint is not binding, this problem is easy. You can just compute analytically the solution. The solution will have x distributed over the whole space, and the conditional density of y given x will be e to the alpha u of x minus y. If y and x are one-dimensional and theta, the cost of information, high enough, you get a discrete solution. It's just set x equal to e of y. Pay no attention to any information. If the information is expensive enough, it may not be worth collecting it. When theta is small enough, the distribution has full support. In fact, in the one-dimensional case, as soon as you start collecting any information, the X has full support. X distribution has full support. When X is multidimensional, so we're tracking several Y's with several X's, it's again true that for a large enough information cost, you just set X equal to the expected value of Y. But now, as the information cost drops, the first thing that happens is you start collecting information about one dimension of variation in Y. So if you think of sigma, the covariance matrix of Y, as W prime lambda W, where lambda is the eigenvalues. It turns out that you want to pick that if your objective function is just the sum of squared errors, that you want to start by collecting information about the linear combination of Y's that has the biggest variance, and that's the eigenvector of the sigma matrix that corresponds to the biggest root. So the other dimensions of variation you will collect no information on. That means your decisions will range along a one-dimensional set in X space, because it will be reacting only to one. You're collecting information only about one dimension of variation. As you lower the information cost, you start collecting information about the second biggest eigenvector of the sigma matrix as well. And your behavior starts ranging over a two-dimensional space, et cetera, until finally at low enough information costs, if this is assuming your objective function is just the sum of squared errors, your conditional distribution for Y given X will make them IID normal with a common variance. And your X's will be continuously distributed. This is in the version of this problem where sigma is diagonal and the sum of squared X minus Y's is the objective function. This is what's classically known in the information theory literature as the water filling problem. We've generalized it. I'm not sure, I don't think I've seen it in the information theory literature, but I haven't really perhaps searched hard enough yet. We've generalized to a case where both the objective function weights A and the sigma matrix can be arbitrary positive semi-definite matrices. And there you still get the one-dimensional, then two-dimensional, then three-dimensional, et cetera, behavior. Looks like I may finish in time to even entertain a couple of questions. So these are conclusions. Stickiness is pervasive in economic behavior, and attempts to model it as due to high physical costs of rapid change are, I think, mostly misguided. I think when most of us think about menu costs or adjustment costs, we're thinking that a lot of it has to do with, I don't have time to worry about that, or it's just not worth paying attention to doing the calculations I would need to react to that. After all, a rational agent, since the interest rates follow time paths that look non-differentiable, that is, they jump all around, we should all be looking up the interest rate every morning and adjusting our consumption flows to what we see. Of course, the adjustments would be very small, and the effect on our utility would be negligibly small. But if we were rational agents, we would be doing that. But we don't. Most of us don't know what the interest rate is unless we're about to buy a house or making a decision as to which bank to choose for our checking account and so on. I think stickiness is pervasive, and stickiness due to inattention, to not tracking information that would really be physically easy to get, is a common source of sluggish behavior. And whether stickiness is due to adjustment costs or instead to information processing costs may have policy relevant implications for calculating the cost of business cycles, and importantly, for predicting the effects on behavior of policy changes or exogenous changes in the stochastic environment. For example, the standard rational expectations approach to modeling the effects of a change in the policy rule will not be correct if it's based on physical adjustment costs. The traditional thing is you estimate a rational expectations model on one period, estimate the deep parameters, including the adjustment costs. Then you say, I'm going to change my policy rule to something else. It's going to change the stochastic processes, but the deep parameters stay constant. But what this theory says is that in times when macroeconomic variables are very stable, people may be totally ignoring them. They may make no adjustment at all in response to variation in interest rates or inflation. Or if they react, they may react very slowly and very rarely. And this does not reflect the fact that it's costly physically to process information. It just reflects the fact that the value of processing this information is low, and the value of processing information about where to go for lunch is much higher. But then you change the environment to one where macroeconomic variables are starting to oscillate wildly, and it may suddenly become much more valuable to spend some of your information processing capacity on looking at those variables. But if you've estimated your model of behavior from this period where everything is so sticky, you may get an estimate that says information processing, the adjustment costs are very high because people never seem to adjust their behavior in response to price signals. But you then have the wrong model for doing the traditional Lucas critique proof analysis of policy. So where do we go from here? Models in which agents optimize subject to Shannon information processing constraints are at this point hard to solve. All the ones that are explicitly solved, even numerically in the literature, almost all of them, are decision problems for individuals. Things get really nasty if you try to do general equilibrium this way and have stochastically varying prices that nobody actually is looking at all the time. So they can't move around and make markets clear because most people aren't paying attention to them. You have to start thinking about, well, there must be some agents who are paying attention to prices, other agents that are not. Those are really hard problems. Mashkowiak and Wiederholt have a couple of New Keynesian-style DSGE models in which they do general equilibrium, but to make it manageable, they cut the economy up into sectors, and one side of a market is subject to information costs and the other side isn't. And that can make it manageable to solve these problems. But I think the interesting question is, suppose neither buyers nor sellers are paying attention minute by minute to the prices. How exactly does that work? So I think we should be studying these models and their properties and trying to figure out better ways to solve them. But in the meantime, I think it should give us more respect for models with ad hoc inertia that's qualitatively motivated by information costs. Such models could be more reliable than models that try to micro-found inertia, quote micro-found inertia, using physical adjustment costs. And then research on cheap approximate methods of solving models with information processing costs would be valuable. And I guess one more thing that I don't list here is somebody really attacking the general equilibrium problem with information costs. I've been trying to get graduate students to do this for several years, but they all realize quickly that this may be a way to make their thesis take 9 years, so they switch to something easier. So those of you with tenure should think about this. I guess we have a couple minutes I could entertain any questions. Okay.